that was the intro to my video. So we're going to do acid-base titration notes. And again, these are a little old, but they should work for what we need to do here. Here's the issue with this one. I do not know how they're going to test this year. Okay? So what that means is I kind of have to prepare you for every possibility, which means I need to talk to you about the new stuff that's in the AP curriculum, and I need to talk to you about the old stuff because it's ambiguous to me. Maybe someone out there understands it, but it's ambiguous to me whether they're going to have you do the calculations that you used to have to do or not, or maybe it's going to be a little more conceptual. So I'm going to make sure you understand the conceptual stuff. And that's where you probably need to go through this reading guide and make sure that you actually hit everything in the reading guide. If we have time, I'll talk about some of the essential knowledges. But at the back of that reading guide, it's got all the essential knowledges that are in this particular section, and you can almost learn more of the conceptual stuff from just reading that than you can from the book even. Okay? So I would just take a both-and approach with this one, just to be on the safe side, because I really don't know exactly what the test is going to look like in terms of this. It kind of could be anywhere. So just to make sure you're prepared, I'm going to go through the old stuff, and that's the majority of what this video will be. And then as far as the new stuff, we'll hit that more when we go through the activity that we do tomorrow in class and maybe some of the practice problems. Okay? So that's kind of the strategy I'm taking here. Hopefully it will work. When you do an acid-base titration, we've already done these this year, right? So you kind of know some of this already. A titration is adding a base with a known concentration to an acid of unknown concentration. That's usually the way that it's done. You add the base to the acid, but not always. So normally your titration curve is going to look like this, right? Because your pH is going up since you're adding acid. Since you're adding base. Let's be careful to say everything right today. But every once in a while you can add an acid to a base. That will work also. But you're going for the equivalence point, okay? What we have talked about so far in this class, the only titrations we've done are strong acid, strong base titrations. I think we did hydrochloric. No, we didn't. Did we do hydrochloric and sodium hydroxide? We did Rolaids, didn't we? Yeah, we did the Rolaids versus the Tums. That's what this lab was the titration lab. Yeah, so we used hydrochloric acid. And I think the Tums had a strong base in it. I think it was magnesium hydroxide maybe, something like that. Anyway, so it was a strong acid, strong base titration, okay, which gave us a fairly sharp, steep curve if we had graphed it. Now, I don't think we actually graphed it on that one. I think we just figured out how much of that, we back-figured how much of that acid got neutralized and then figured out which one of those two worked better. So what we're going to do for the lab we're doing at the end of this week is an actual titration curve where you're looking at the pH at each given moment throughout the titration, and you're going to actually graph it. What you're going to notice with the strong acid, strong base titrations is that they have very steep curves. With the weak acid, strong base titrations, the curves are not so steep. Okay, and we'll talk about what that means. But equivalence point is the point where you have an equal number of moles of acid and base in the solution. And then your titration curve is just the graph of the change in the pH. Okay. You need to think about this in 4 main stages. Now, your book still teaches it this way. Okay, so this is basically right along with what the book says. And we're going to look at that for several different types of titrations. The two that we're going to focus on here are strong acid, strong base, what happens there with the titration curve, and then a weak acid, strong base titration. Okay? So the first thing you want to look at is, whoops, I thought that highlighted these afterwards, but I guess it doesn't. Initial pH. So what is the pH of the solution before we've added any base into it whatsoever? And that's not all that difficult, okay? Between the initial pH and the equivalence point, how do you figure out that pH? At the equivalence point, now at the equivalence point is not all that difficult either. And then after the equivalence point, how do you find the pH? Okay, so those are 4 different stages in a titration, and there's actually a different type of calculation you have to do for each one of those stages depending on where you are. Okay? This is also in the book, and I think in the reading guide I tell you should probably write down these stages. So, sorry I can't stay on this longer, but I got to make sure this isn't a super long video. So this, again, this is a strong acid, strong base titration curve. This is what it would typically look like. Notice how steep the curve is, right? You've got this huge change in pH all of a sudden, this big jump, okay? And you guys saw this when you were using phenolphthalein as your indicator. You add 1 drop of base, and all of a sudden it's completely pink now, right? And that's showing huge pH change. Yes, sir?
If methyl red, does that go to clear, or does it go to orange?
No, I think methyl red actually changes from an orange to a more yellow. It might eventually go clear, but you're going to see...
Like, why don't we use both methyl red and phenolphthalein whenever it gets clear? Just go let go.
Well, okay, so that's a good question. The reason, I mean, another question that might come from that is, why did we use phenolphthalein if it doesn't change color until a pH of 9? And that's not really showing us a neutral solution, is it? But the reason why is because, I mean, notice where this curve happens. I mean, there's no change in volume here, right? So from 50, really from 49.5 to 50, that's when you're going to get this huge jump in pH. So for a strong acid, strong base titration, it doesn't matter that much which indicator you use, as long as it's somewhere in this steep climb here. So we could use methyl red just as easily as we could use phenolphthalein. I think phenolphthalein is a little bit easier to see because it's easier most of the time to see a clear solution turn a color rather than see a colored solution get clearer or lighter. Okay, so that's why we use the phenolphthalein. All right, so strong acid, strong base titration, that's like sodium hydroxide plus hydrochloric acid. That's really easy. The initial pH, to calculate that, you just figure out the initial concentration of your strong acid. And we've done these calculations before, right? So if I start with 0.1 molar hydrochloric acid in my titration, what is the initial pH of the solution? You can do this in your head if I write it a different way. Now wait, can I say that? This is the concentration of HCl. Can I say that's also the concentration of the H+? For a strong acid, yes I can, because it completely dissociates, right? Okay? But if it's 1.0, I guess I should have said 1.00 there, times 10 to the negative first molar H+, then what's my pH? What happens if you take the negative log of this number? Just 1, right? Okay, and you can see it when you write it with an exponent, okay? It's just going to be whatever the exponent is, as long as this is the number 1, okay? So your pH here is what? 0.000. Because you need the 3, right? Only the numbers after the decimal point are significant. We had 3 significant figures up here, okay? So that's it. That's pretty easy, right? For a strong acid, figuring out the pH is not hard. Between the initial pH and the equivalence point, the pH is determined by the concentration of acid that hasn't been neutralized yet. Here's where it gets a little bit tricky, okay? Whoops. Well, why didn't I put an example for that one? Sorry, hang on just a second. How was I okay with these notes last year? I don't understand. Okay. We'll come back to it, because there is a practice problem that covers this. Oh, actually, I guess there's one there, too. I didn't see that. Okay. So between the initial pH and the equivalence point, I'll show you how that works in just a minute, okay? But basically what you have to figure out is how much of the acid hasn't been neutralized yet, okay? So you figure out, okay, so I've added this much sodium hydroxide. It's going to react with this much of the acid. How much has not been neutralized, and that's going to determine your pH, okay? At the equivalence point, really, really easy with a strong acid, strong base titration. Just write this number at the equivalence point, okay? For strong acid, strong base titration, when you get to the equivalence point, then the pH is 7, because what you have, the only thing left is something like sodium chloride, right? And this is true for any acid, strong base that you could combine together. You're going to have two ions floating around in that solution that don't affect the pH at all. Na plus doesn't affect the pH, Cl minus doesn't affect the pH, so it's just 7, okay? So that's easy for the strong acid, strong base. And then after the equivalence point, then you just figure out, well, how much extra base have I dumped into this thing? And then you calculate your OH minus concentration, and that'll give you the new pH of the solution. Does that make sense? Everybody with me? Okay. So practice problem here. Calculate the pH when the following quantities of 0.1 molar NaOH have been added to 50 milliliters of 0.1 molar HCl solution. So 49.0 milliliters and then 51.0 milliliters. All right, so when we've added 49.0 milliliters, now notice these two concentrations are the same, right? Okay, so when I've added 49 milliliters, where am I in this titration? What stage am I at here? Just before the equivalence point. Because remember, the equivalence point is when you have equal number of moles of the base and the acid, right? Okay, and if you want to really calculate this through, you could figure out how many moles of the sodium hydroxide you have versus how many moles of the HCl you have, right? So if I want to figure out my moles of sodium hydroxide, I just multiply the molarity times the volume, and the volume has to be in liters, okay? So my moles of NaOH equals 0.0050, is that right? 3 times the 0.1, yeah, that's right. So that's how many moles of the NaOH that I have. The number of moles of HCl that I have at this point is, whoops, I'm sorry. It's 50 milliliters of the HCl solution. I've only added 49 milliliters of the NaOH at this point, so it's 0.0049. So then the moles of HCl would be 0.0050. Okay? So then you could do this like an ice table if you want to, or you could just kind of think about it. But the reaction that's going to happen here, basically the net ionic equation for any strong acid, strong base reaction, H plus OH minus yields H2O. That's for any strong acid, strong base. Do you guys remember that from last year? I don't know if we talked about it this year or not. But so if I've got 0.0050 moles of this and 0.0049 moles of this, then what's going to happen here is this is my OH minus is my limiting reactant here, right? So all this gets used up. I'm left with 0.0001 moles of the H plus, okay? And that's it. The rest of it has, reacted together, been converted into H2O, which we don't care about at that point because it doesn't change the pH. So this is all I have left of my H plus, which can be written in another way. 1 times 10 to the negative fourth moles. Well, actually, that doesn't really matter at this point. But I want to know the pH of that solution, right? So here's where you have to be a little careful. This is the number of moles, not the molarity, right? I need to divide that by what? Of 99 milliliters, right? Because we added the two of them together, right? The 50 milliliters of the HCl and the 49 milliliters of the NaOH. So you've got 99, which, again, you have to change that to liters, so 0.099 liters. Okay? So when you do that, that'll give you your concentration of H plus that we have left. Which is 0.001, let me see if these are working, 301. Okay? So that's your concentration of H plus. You take the negative log of that number and you get 2.995. So the pH equals 2.995. Okay? So it's come up from 1 to 2.995, which is, you know, it's a jump, but it's going to be interesting to see when we get to 51 milliliters how much it's jumped at that point. So then for this next one, we've got 51 milliliters. So our situation here is now we have 0.0051 moles of the NaOH instead of 0.0049. Okay. So now the OH minus is not my limiting reactant anymore. The H plus is. All right? That's what I'm going to run out of. Let me change this. I'm cheating a little bit. I know you guys can't do this on your paper, but I'm just doing this for the sake of time. So now our limiting reactant is the H plus. Which leaves me with 0.0001 moles of the NaOH. Okay, so then I can do the exact same calculation here for the OH minus. So this is my molarity again for the OH minus. But the difference now is that this is not a pH anymore. When I take the negative log of this number, it's a pOH. Huh? Oh, yeah, I'm sorry. Your volume does change. Thank you. I was trying to be lazy. It didn't work. So now we've got 0.101 liters. So that does change your number a little bit. Now 9.9. 90 times 10 to the negative fourth. Okay, so then our pOH is actually going to be a little bit different here. You take the negative log of that, you get 3.004. So then I subtract that from 14, that'll give me the pH, which is 10.996. So in the space of 2 milliliters, we went from a pH of 2, more than 2, 2.9, is that what we said it was, 2.9 something, to a pH of almost 11, okay? Which makes sense because you guys have added a drop before and had that pH skyrocket, right? So you had 2 milliliters and you're way past the equivalence point at that point. That's so pink you're not getting it back by breathing into it, okay? It's not going to work. All right, so does that kind of make sense how you make those calculations? Again, at the equivalence point, it's very easy. At the equivalence point, the pH would be 7 because it's a strong acid, strong base, okay? All right. And we talked about this already, why you can use phenolphthalein or methyl red. Either one will work fine. Strong base using strong acid would be the same, but backwards. Okay. So now we're going to talk about weak acid strong base titrations. Now notice this is the graph for the weak acid strong base titration. Okay, and there's a couple differences you might notice here on this graph. What's one of the things that you notice right off the bat? What's smaller? Okay, starts higher. So in other words, the pH is higher to start with, right? Which, does that make sense? Yeah, that makes sense because it's a weak acid, right? The other thing you would notice is that the curve is less drastic. It's less steep here at the equivalence point. Now, there's one other thing that you might notice here. Where is the equivalence point on this one? What? The pH at the equivalence point is not 7. Well, why is that? We'll talk about that. Okay, so again, we have the same 4 stages happening in this titration, okay? But to find the initial pH, you find the pH of the weak acid. And I'm going to fly through this because you guys have been doing this for the last 2 units at this point, okay? So if I want to know the pH of a 0.1 molar acetic acid solution, what do I do? Can I say that's 0.1 molar H+? No, because most of this doesn't dissociate in water, right? Because it's a weak acid. So what do I need to know in order to be able to figure this out? I need to know the Ka of acetic acid, which, if I'm remembering right, I think it's 1.8 times 10 to the negative fifth. Okay? Now, I'm not going to work this one out because, like I said, we've done problems just like this for the last 2 units. But it's basically you're setting up an ice table, right? And then you're going to end up with the 1.8 times 10 to the negative fifth is equal to x squared over 0.100, right? That's the end result of one of those ice tables. So then you solve for x. That will give you your H plus concentration, and then you can take the negative log of that and find the pH. Okay? So that's what you do before you've added any base. All right? Here's where it gets a little tricky. Between the initial pH and the equivalence point, what is happening is you're adding strong base. So if I'm adding strong base, I'm adding hydroxide, right? Adding OH minus plus this one's acetic acid, right? So HC2H3O2 is what I've got in there. Well, what's going to happen there? It's going to make H2O, right? Because this hydrogen is going to come over here. So now you make water and C2H3O2 minus. Huh. Interesting. So we're kind of making a buffer solution here, right? By adding this base in there, we're turning some of this acid into its conjugate base, which is actually what you did on the Ka lab. You remember where you added half and half after you had changed the acetic acid into sodium acetate? Or maybe it wasn't acetic acid. I don't remember what we used. Anyway, whatever it was. So that's basically what's happening here. You're making some of the conjugate base, okay? So guess how you calculate the pH at that point, if it's basically a buffer solution. Henderson-Hasselbalch, right? So then what you do, you think about the Ka of your or acetic acid, okay, which we just said was 1.8 times 10 to the negative fifth. Pretty sure if you take the negative log of that, you end up with 4.74, okay? So then you've got your 4.74 here. Figure out what your concentrations of your acid and your base are now, okay? So then you have to think about, well, how much of the base did we add? Okay, so and then how did that change these 2 concentrations? Once you know that, you can plug it in here, and then you can find your pH. Okay? So after you've started adding some base to it, but you're not to the equivalence point yet, that's going to be Henderson-Hasselbalch. Okay? The first step there, though, is you have to do stoichiometry to figure out how much of this and this do we have left. Okay? So that's the tricky part that we need to talk about in an example. But then the equilibrium calculation, use Henderson-Hasselbalch. Okay? This is probably a good thing to think about. Stoichiometry first, equilibrium second. All right? When you're talking about this step in a weak acid strong base titration, do your stoichiometry first, then do Henderson-Hasselbalch. We are seriously running out of time here. What I may have to do is do this video in 2 parts, do the second part at home, and then I'll just post it. You guys have until, when do we start a new section? I think we don't start another section until Friday. So, and you don't have a quiz on this until next week. So you've got some time to figure this out. But I think that's probably a good stopping point right now, is just talking about that. Unless Yeah, because then I got an example here. So we'll stop there. I'll finish this video at home so that you guys can kind of figure out what to do. And I guess we'll see you guys in class tomorrow.